the CISPA Helmut Center for Information Security and a professor for computer science at Saarland University. He obtained his PhD in 2003 from Stanford University, and since 2003 leads Helmut Center for... someone said something? Couldn't hear if someone corrected me. Since 2003, Bernd leads the Reactive Systems Group, which became part of CISPA in 2020. And his research focused on development of reliable guarantees for the safety and security of computer systems, including specifications, program synthesis and repair, and static and dynamic verification. Today, we'll talk about model checking hyperproperties. As you may know, most verification efforts focus on trace properties, but many policies like information flow cannot be expressed by trace properties, as they relate several traces that are captured by hyperproperties. Therefore, hyperproperties are very interesting. And I leave the stage for him for the rest of his talk. Bernd, the stage is yours. You can share your screen.
Thank you very much, Yakir. First of all, thanks very much to the organizers for this great invitation. I'm very honored to be here. I'm very sad not to meet you in person, but I have to say it's a little bit fun to play with these Zoom tools. So I'll ask for your patience a little bit because I want to try out this this feature from Zoom that allows you to put the slides in the background. So I think this is neat, but it takes like a few seconds to start up, I think. Yeah, so maybe somebody can let me know when slides start to show up, because I think it is kind of slow.
The slides are up.
Oh, okay, excellent.
Yes, we can see them.
And you can also see me, hopefully. Then we can get
Yes, you are part of the screen, yes. It works as planned.
Wasn't that worth it, waiting for a minute? All right, so this talk is about hyperproperties, which, as you probably know, are a generalization of trace properties. So our normal bread and butter in verification, I guess, is to prove that certain program assertions are true or invariants are true, or that a program terminates, or that there is a limit on the response time. All these things are trace properties. Now, one reaches the limit of trace properties if one wants to say something that is common to multiple traces, or that specifies a relation between traces. So a very mild generalization from liveness would be liveness with promptness, where you, for example, say that it doesn't suffice that you eventually terminate, but rather there should exist a bound on the number of steps until which you terminate, right? So this is promptness, and this would be a hyperproperty because it requires the existence of one bound that works for all traces. Maybe more fundamental properties that have to do with knowledge are hyperproperties, because an agent knows something if it's true on all traces that the agent can't distinguish from the one he has seen, right? So again, this is a property that relates traces without exactly saying what needs to happen on those traces. In cyber-physical systems, we have notions like continuity and robustness. Small deviations in the input lead only to small deviations in the output. And then there is the big domain of information flow properties. If I want to say that some information is flowing, then I want to say that an observer can notice a difference, and maybe I'm only interested in the existence of such a difference without saying exactly what the criterion is for noticing that that something happened. So on this general level, all these properties can no longer be expressed as trace properties. They need hyperproperties. Now, the term hyperproperties was coined by Clarkson and Schneider, and they made this definition that a trace property is one where the trace property is satisfied if the traces of the system are contained in a given set of traces, which we call the trace property. And a hyperproperty is a set of sets of traces. And now we say that the system is correct if its set of traces is an element of this hyperproperty. Now, I think that hyperproperties are so exciting because they allow you to express properties about your system that aren't your normal functional properties, but that are really important nevertheless. I mean, the one area where this is sort of commonly understood is security. If you think of all these recent attacks, Heartbleed, Meltdown, Spectre, the common feature is that the attacker gained access to some information that he should not have gotten access to, right? So this is a violation of non-interference. More formally, we have a security critical system, which is described as having high security inputs and low security inputs, and correspondingly high security outputs and low security outputs. And the issue we have is that there should not be a dependency from the high security inputs to the low security outputs. So the system may, of course, process even secret inputs, but it should only produce results that depend on these high security inputs as also high security outputs. Low security inputs may go into either computation, but there should not be a dependency of the low security outputs on the high security inputs. So as a hyperproperty, this means that if you're looking at two traces that are the same with respect to the low security inputs, then it must be the case that they are the same with respect to the low security outputs. But just to show you that security is not the only domain where properties of this type arise, think of error detecting codes. Say we have an encoder that takes some data and encodes it such that it can go over a unreliable channel. Now, an encoder will typically put in some redundancy into the encoding so that small errors won't affect the transmission of the data. And one such property might be that different data should be encoded at least with a certain Hamming distance to each other. So again, as a hyperproperty, for all traces of our system, I want to make sure that the Hamming distance of the encoding is beyond a certain threshold. I don't have access to multiple encodings directly because they happen in different computations, and I don't want to say anything about the specific code that's being used other than that it satisfies a certain Hamming distance. And lastly, there is the whole issue of symmetry and fairness. So say you're designing an arbiter or a bus protocol or anything of that sort that deals with multiple clients. Now, what you want to say is that I don't give preference to one client over another unless, of course, there's a justified reason for doing so. So an example property of this nature would be that if we look at two traces that are symmetric to each other, that is, the requests from one client in the one trace are the requests of the other one in the other trace, then it should also hold that the behavior of the arbiter is the same, just flipped in the two situations, right? So that means that the behavior of the arbiter should depend on the pattern in which the requests are made, not on something else, such as the ID of the client. All right. Now, there are, of course, many strong verification and analysis techniques for hyperproperties. In particular, in security, we have type systems, we have proof systems for behavioral equivalences. There are lots of dynamic techniques that do, for example, taint tracking, and in that way provide an assurance that there's no illegitimate information flow. And then there are program analysis tools like Joanna that can also handle properties like non-interference. So I don't plan to go into too much detail into these specific verification techniques, mainly for the reason that most of them are what I would call single property techniques. They're specialized procedures that address one particular important hyperproperty. Now, the topic of my talk is to try to come up with a unifying framework for hyperproperties, because hyperproperties play such an interesting role in so many different domains that it seems tempting to avoid over and over reconstructing verification approaches based on the same principles. The question really is, can we do the same trick that worked so well in model checking of trace properties, where we have general logics and general uniform algorithms? So to what extent can we do the same thing for hyperproperties? So what I plan to do in this talk is, first of all, in the first part, try to clarify the landscape of hyperproperties, and we will use specification logics as a guideline to organize this space. So we'll look at various logics that can be used to describe hyperproperties and compare them in terms of expressiveness and also in terms of the decidability and complexity of the model checking problem. And then in a shorter second part, I want to talk a little bit about tool development, mostly for model checking, but also for problems like satisfiability, monitoring, and synthesis based on these insights. All right, so the starting point are the temporal logics. In model checking, of course, logics like LTL and CTL star are very popular. LTL specifies computations. We might, for example, say eventually globally x is 0. That is, from some point onward, x is 0. And CTL star would be an example of a branching time temporal logic, where we could say things like it's always the case that there's a path where eventually x becomes 0. Now, these logics are organized in a nice and clean hierarchy. So one of the basic facts we know is that LTL characterizes exactly the non-counting omega regular properties. If you want to have the full omega regular properties, then you can add quantification over propositions to LTL that then gives you QPTL. Now, there's also the correspondence between the temporal logics and first order logic. So we know that LTL is equivalent to the first order logic of order. This is the famous Kamp's theorem. And in a similar manner, we know that QPTL and monadic second order logic of one successor, S1S, are equally expressive. Now, on the branching side, we have CTL star, which happens to be equally expressive to monadic path logic, which is monadic second order logic, where the second order quantifiers are restricted to refer to full paths in our Kripke structure. And then when we add quantification over propositions to CTL star, then we get monadic second order logic. Now, starting with this very basic picture, we'll create logics for hyperproperties. Now, we use two basic tricks to do that. So first of all, starting from a temporal logic like LTL or CTL star, we can obtain a logic for hyperproperties by adding variables that refer to traces in the case of LTL or paths in the case of CTL star. So the idea is that you want your formula to be able to refer to multiple executions at a time. So if you do that to logics like LTL, CTL star, or QPTL, then you get corresponding logics like hyper LTL, hyper CTL star, hyper QPTL. Now, for the first order and second order logics, you don't actually need to do that, because the quantifiers in these logics already talk about arbitrary points. So these points might occur on different executions of your system. But what you need to do in order to let them express hyperproperties is let them recognize if 2 points, possibly on 2 different executions, happen at the same time. That is, they are on the same level. And this is what the equal level predicate does. So you take the logic like the first order logic of order, you put in an extra interpreted predicate, the equal level predicate, and you get a logic that's capable of expressing hyperproperties. Same thing for monadic path logic or for monadic second order logic with 1 successor. Now, when you do that, then you get sort of a one-to-one correspondence between the logics for traces and trees and the ones for hyperproperties. But there is something interesting going on. So these equivalences in expressiveness that we know so well from the trace logics don't hold anymore in the hyper setting. Rather, we get this somewhat richer hierarchy of logics. And it is this hierarchy of logics that I want to take a closer look at in the following. So we'll just go through the hierarchy one by one and see what happens as we add more features to the logic. We'll start in the lower left corner with hyper LTL. So this is probably the simplest hyperproperty you can think of. It simply says, let's demand that all executions of our system are the same. If our system is this box with a little light bulb on top of it, it just means that this light may blink in arbitrary patterns, but it should blink in the same pattern on all executions. Or more formally, for all pairs of traces and all points in time, the light is on the first trace if and only if it's on the second trace. Now, quite obviously, you can't express such a property, say, in linear time temporal logic. I could express that a certain pattern should occur, right? I could say that the light should be on in the second step and off everywhere else. Or I could say it should be on in the third step and off everywhere else. I could do so for pretty much any pattern, but our property says that any pattern is okay. So my LTL formula would necessarily allow any pattern. And then once I have a system that shows 2 different patterns, like the third one there on the right, then I'm in trouble because LTL has no way of rejecting that system because all the patterns on the paths are okay, but not their combination. So hyper LTL fixes this by adding a quantifier prefix to the logic. So you see the syntax up there. It's the syntax of LTL. The only thing that's new is the first line where we have universal and existential quantification over traces. And then in the second line, you see the A indexed by pi, meaning that the atomic proposition A is now evaluated in the trace indicated by trace variable pi. So I start with my quantifier prefix, and then I have an LTL formula where the atomic propositions can refer to multiple traces that I have set up previously with my quantifiers. So in our little example, that would mean I would say that for all traces pi, for all traces pi prime, it globally holds that on pi is true if and only if on pi prime is true. In other words, all executions have the light on at the same points in time. And you see that in the crypt key structure, that means I step through the crypt key structure twice. I select 2 paths simultaneously, and I synchronously compare them at corresponding positions indicated here by the dotted line, and I check that the light is on in one position if it's on in the corresponding position. Now, this is very neat because with this quantification over traces, I can take, for example, variations of non-interference that you find in the literature and explain them precisely using the temporal logic. So here are a few examples. There's observational determinism, which says that for all traces, for all pairs of traces, it holds that if the traces start with the same low security input, then they must globally exhibit the same low security output. So this is a very simple property with just two universal quantifiers. Now, non-inference has a slightly different pattern. Here we have a for all exists quantifier pattern at the beginning. So this says that for all traces pi, there exists another trace pi prime that, if you look at the second line, that has the property that it agrees on the low security inputs and outputs. So it does exactly the same thing. But the first line says that globally the high security inputs on pi prime must be true. That is, we have set on pi prime, we have set the high security inputs to a constant value, in this case to true all the time, right? And even though we did that, it is possible to recreate the same low security input-output behavior. So the existential quantifier is actually helpful if you have a non-deterministic system that may react in different ways to the same input. And we say that, okay, there is a way to react in the same way as if we hadn't changed the high security input. All right, and one last example, generalized non-interference. There you have a pattern with two universal quantifiers and one existential quantifier. And what it says is that we take the high security inputs from one universally quantified trace and the low security inputs and outputs from the other universally quantified trace. And there must be a third one that combines the two. So no matter how I pick the low inputs and the high inputs, there must be a way to combine them. In other words, again, there's an independence between the high security outputs and the low security outputs and the high security inputs, even though by coincidence, non-determinism might produce different results. Okay. Now, how do we do model checking of hyper-LTL? It's actually not terribly complicated. It's a reduction to the emptiness of Büchi automata. So the idea is that the alphabet of our automaton will consist of tuples of sets of propositions. So one set of propositions characterizes what the labeling on one execution, and we have a tuple of them so that we can keep track of multiple such executions. Now, if we have a quantifier, then we build the product with the Kripke structure and project away one such component. So the product ensures that we select a trace according to what the Kripke structure has an offer, and the projection just eliminates it from the alphabet of the automaton. And lastly, if we need to do quantifier alternation, then we complement the automaton. So to give you an example, let's say we have this property which says that if the inputs are the same, if the inputs are globally the same, then the outputs must globally be the same. So the first thing we do is we negate the formula so that we hunt for counterexamples. So now it's simply, there exists a pair of traces where the inputs are globally the same, and yet the outputs eventually exhibit a difference. And then we start by building an automaton for the inner LTL formula. So the inner LTL formula now refers to atomic propositions for pi and for pi prime. So the alphabet is going to be one of pairs that refer to two copies, one for pi and one for pi prime. But this is the standard construction from LTL to Büchi automata. And then we start eliminating the quantifiers. So we begin with the innermost existential quantifier. So we intersect our Büchi automaton with the Kripke structure. So the choice of the first component of the alphabet is limited to the way a particular trace in the Kripke structure would resolve it. And then we project it away from the language of the automaton, which results in a one-tuple alphabet, namely now just the propositions from the remaining component of the tuple. And then we do the same thing again for the outer existential quantifier. Again, we intersect with the Kripke structure. Again, we eliminate the component from the alphabet, and that results then in a one-letter alphabet. And that means now we have an automaton that runs on the one-letter alphabet, and that is non-empty if and only if there exists a counterexample to our specification. Now, as you noticed, there is the standard construction for LTL in there, the construction of building an automaton from an LTL formula. But there is also this complementation that we need to do when there's a quantifier alternation. I've only shown you what happens with existential quantifiers, but of course, if you have a universal quantifier, you can represent that as not exists, not subformula, and that means the automaton for the exists subformula needs to be complemented to get the automaton for the not exists formula. And this results in the following complexities. So as long as we don't have quantifier alternation, this is exactly like normal LTL model checking. So it's a non-deterministic log space in the size of the Kripke structure. Every quantifier alternation will cause an exponential blowup because of the complementation. So if you have one quantifier alternation in there, then that's P space, and then it becomes K X space as you get more alternations. Now, this may sound really bad at first glance, but in practice, it turns out not to be so terrible. One reason is that most of the properties we're interested in are actually far high up in this hierarchy. So observational determinism had only two universal quantifiers, so it's alternation free. So this is in n-log space. Non-inference and also generalized non-interference actually have one quantifier alternation, so they are p-space complete. But there really aren't that many properties of interest that have a higher alternation depth. And there is one other piece of good news, that is if you analyze the complexity more closely in the shape of the Kripke structure, then you find that it drops significantly if you have simpler shapes. In particular, if you're looking at trees, then it drops to log space no matter what the quantifier alternation. And I'll get back to that in a while, but this is actually very good news for runtime verification, because in runtime verification, you are not given a system up front, but rather you build it up as you make observations of your running system. And very often you construct a tree as you do that. And this means that you can, after seeing one more trace, you repeat the model checking, but the cost of that actual model checking run is only a log space. So for applications like this, this is actually very, very efficient. All right, a few comments about satisfiability. Now, obviously, satisfiability is of great interest because you want to compare different hyperproperties that you may think are the same or where you don't know what the exact relationship is. So a typical example would be that you have these two versions of observational determinism. The first one says that if the inputs are globally the same, then the outputs must be globally the same. The second one says that, well, the first difference in the output can only occur when there was a previous difference in the inputs, right? So you find both definitions in the literature, and of course you want to know whether or not these are equivalent definitions of observational determinism or not. Now, if you have a quantifier, a formula without quantifier alternations, then satisfiability for hyper-LTL is exactly the same as for LTL. All you do is you replace the atomic propositions with the indexes that refer to different traces, just with different copies of the atomic propositions, and then you're back to LTL satisfiability. So this is p-space complete, just like LTL satisfiability. If you have exists for all formulas, then things become a little bit more tricky, but not much. So the insight here is that if you have a formula that exists and then for all quantifiers, then it suffices to find a model that has at most one trace for every existential quantifier. And based on that insight, what you do is you simply unroll the universal quantifiers over the existentially quantified variables. That gives you an exponentially larger formula that is, however, equivalent with respect to satisfiability. So if you have an exists for all formula, then you get X-space completeness for the satisfiability problem, which is a bit expensive, but still okay. And in particular, what you can do in this fragment is look at implications and equivalence of alternation-free formulas. So if you have two universally quantified formulas and look at their implication, then that falls into that fragment. And this actually is a large portion of the formulas you're interested in. Now, unfortunately, if you have for all exists, then things become a lot messier. So just to give you a small example, what you can do in this fragment, you can say, I want to have eventually an A, and if the second line says I only have one. So if I have an A at some point, then there won't be another A. And the third line says that if I see an A on one trace, then there must exist another trace where the A happens one step later. So in other words, I can easily demand that there are infinitely many traces that just have the A at later and later positions. And actually, it turns out that you can easily encode computations of Turing machines in this manner. So as soon as you have a single for all exists quantifier alternation, the logic becomes undecidable. So in terms of satisfiability, this is the picture. Exists and for all, the alternation-free fragments are simple. The exists for all fragment is X-space, but still decidable. But as soon as you have a signal for all exists alternation, it becomes undecidable. Okay, so let's move a bit on in the hierarchy. So we go from hyper-LTL up to first-order logic of order with the equal level predicate. So in the trace setting, first-order logic and LTL are equally expressive. Here we see a difference because we add this equal level predicate. So the logic is simply monadic first-order logic of order and this extra predicate. So we interpret this logic over a domain of pairs where the first component identifies a trace and the second component a point in time. And then less than just means that the time component is greater, right? So we have Tn and Tn prime. So we are on the same trace, but we are, n prime is greater than n, so we are at a later time. And the E predicate says that we may be on different traces, so T may be different from T prime, but we're at the same point in time, so the n is the same. So for example, if you wanted to say that all executions have the light on at the same times, you would say that for all x and for all y, if they happen to be on the same level, that is E of xy, then the on predicate should true for X if and only if the on predicate is true for Y. Now, the reason this is more powerful than hyper-LTL is that hyper-LTL forces you to first quantify over the traces, and then you have the temporal modalities to talk about time. And here you can mix things up. So for example, I can say there exists a point in time X such that all points that happen to be on the same level as X have the light on. So I can say that there exists a point in time where all the executions are on, which I can't do in hyper-LTL, because in hyper-LTL I can only compare a constant number of traces, never the entire set of traces. So that means the first order logic is strictly more expressive than hyper-LTL. Now we go one more step to hyper-QPTL. So we add quantification over propositional variables to hyper-LTL. Now this gives us back the ability to fix a point in time that is common for all traces, because now we can start by quantifying over an extra proposition before we look at different traces. So in hyper-QPTL, this property would look like this. We say that there is a way to evaluate Q such that for all traces pi, it holds that, well, there is a prefix, a possibly empty prefix where Q is false, but eventually it becomes true, right? This is what the until says, not Q until Q. And when that happens, when the Q first becomes true, then it must also hold that on is true on my trace pi, right? So by having this Q as an extra marker, I can say that there is a common point in time where all must agree on the value of on. Now, it's easy to see that hyper-QPTL is more expressive than first order logic. And that's because if we restrict to just single trace models, then we're back in the trace world. And that means there hyper-QPTL corresponds to QPTL, which corresponds to the omega regular languages. And first order logic corresponds to, well, first order logic, the equal level predicate is useless. And there it corresponds to LTL, which is weaker than the omega regular languages. So just by comparing it in the trace setting, we see that because QPTL can express all omega regular properties, LTL cannot, that hyper-QPTL is, again, strictly more expressive than first order logic. So what we can do now is count, which means that if we want to, we can say things like, at even times, all executions have the light on, right? So we use the quantification over Q as a marker, whether we're in an odd or even time position. And then we say that, okay, if Q is true, then the light must be on, right? And Q will go on and off to implement this even odd marking behavior. So this is something you couldn't do in first order logic. Now, what about model checking? It turns out that the same algorithm pretty much still works, because now with hyper-QPTL, all we have added is the possibility to add this extra trace that just interprets the new proposition. So we just add a way of quantifying over that new propositional variable in order to implement an existential quantifier. And other than that, the algorithm stays exactly the same. All right, one more step, S1S. We have monadic second order logic with the equal level predicate. And it turns out that if you reach that, then things become much more powerful. So now we have S1S plus the equal level predicate. we can still say things like at even times all executions have the light on. So now we quantify over a second x and say that, well, the initial position is in that set, so O of y is implies that O is an element of this x, and it goes back and forth according to the level. So if y is an x, then the successor of y is not an x, and so forth. And we eliminate, we emulate the behavior of the previous property. Now, unfortunately, now the model checking problem becomes undecidable. Now the logic is so powerful that we can actually encode the halting problem of two counter machines. So the idea is that we can encode a configuration of a two counter machine simply by setting markers in the different positions corresponding to the counter values, and then we can characterize a set of such traces as the interpretation of a second order variable, and let the Kripke structure produce all possible configurations, but the second order variable identify those that are involved in the computation. And as long as this is predecessor closed and it includes a halting configuration, that then is evidence for the halting of the counter machine. All right, so this is the story in the linear time setting. By the time we reach S1s, the model checking problem has become undecidable. However, we have gone pretty far before that happened. So we have gone all the way to hyper QPTL, and only this last step made it undecidable. I noticed that I'm running a little bit low on time, so I will go well quickly through the branching time setting. So what happens if we add branching time? So hyper CTL star is CTL star plus path variables. It's a very similar idea to the extension of LTL to hyper LTL, except that now the quantifiers refer to paths rather than traces. Hyper LTL is sort of a syntactic fragment where we don't allow nesting. So we have a quantifier prefix, so no quantifiers in the scope of temporal operators. And of course, CTL star is also a fragment of hyper CTL star, namely the fragment where we only have one variable. We can't refer to multiple paths at the same time. So what you can do with this is talk about the branching behavior and about the flow of information at the same time. If you look at this example, so it starts with a Boolean y, and this is not specified what its initial value is. So it could be true or false. So in the Kripke structure, that gives us two branches. Then x reads a secret value, which means that now there is something to be worried about. But then in the third line, it outputs only the non-deterministically chosen value of y. And so we get this Kripke structure that you see below, where there are different outputs, namely based on the value of y, we may see an output O or not O, right? But the output is actually independent of the secret being read in the second line, because once you're in the left branch or in the right branch, it will be one definite value O or not O that's being output. So this is a example for a program that doesn't leak any secret information, and yet it might appear to you that it leaks information if you just look at the traces rather than at the branching structure, because the correctness says that once you do the reading, there will be no difference in the observable output behavior anymore, even though globally there may be different outputs. And this is exactly what a logic like hyper CTL star can do. It can say that once you do the reading, globally, if you do the reading, then it holds for all subsequent paths that the observable output is the same. All right. Now, surprise, surprise, the model checking is, again, more or less the same as before. All we have to change is that rather than talking about sets of propositions, identifying the trace, we now talk about states, so we can actually track where we are in the crypt key structure. But other than that, we handle quantifiers by building the product with the crypt key structure and projecting away the respective component from the alphabet, and we still use complementation to handle quantifier alternation. So it is the same type of algorithm. As you eliminate quantifiers, your alphabet becomes smaller. Once you have reached the closed formula, your automaton has the one-letter alphabet, and the existence of a word in the language is evidence for a violation of your property. Hyper-CTL star satisfiability works also very similar to hyper-LTL satisfiability. Not surprisingly, it's undecidable in general because it contains hyper-LTL as a sublogic. One might worry that formulas of the form exists pi globally, exists pi prime, pi double prime, might be undecidable because that looks very much like a universal quantification with the globally. It will certainly talk about an infinite number of traces that branch off, but it turns out that this is still decidable. So for the satisfiability problem, you get exactly the same result as for hyper-LTL. It remains decidable as long as the quantifier structure exists for all, and it becomes undecidable as soon as you have for all exists. All right, now monadic path logic is one step up. So we have second order quantification where the second order variables refer to full paths in the tree. So for example, we would say that for all paths P1, P2, it holds that for all positions X, Y, and Z, if X is a read position, X is on the first path and on the second path, and Y is on the first path and Z is on the second path, and Y and Z are on the same level, well then the output must be the same. So obviously I can do similar things as in hyper-CTL star because I do have quantification over paths. What's new, however, with monadic path logic is that I can talk about knowledge. So the knowledge modality says that an agent who observes only the propositions associated with him on some path knows that pi is true, that phi is true. So formally, that means that for all paths where the prefix up to position I is the same as on the one that we are currently on, it must be true that the property phi is as well. So this modality cannot be encoded in hyper-CTL star because we don't have access to the past. We need to talk in this modality about all possible paths that could have happened, but our quantification only goes over the paths that start in the position where we are now. So you can't do this in hyper-CTL star, but you can do it in monadic path logic because that always gives you full paths. So you have always access to the entire system. So this means that, again, monadic path logic is strictly more expressive than hyper-CTL star. And the good news is that, again, a small variation of the model checking algorithm still works. So now we do a reduction to emptiness of Büchi automata. The only minor modification is that we need to quantify over both second order variables, which are full paths, and first order variables, which are prefixes of paths because they just talk about a particular position that is reached after a finite number of steps. So I explain in the paper, in the proceedings, in a bit more detail how this works, but it's very simple. You simply add a special symbol that says that you have reached the end of the prefix, and this then identifies the path towards a position chosen by a first order variable. Other than that, the same algorithm that we have seen from hyper-LTL through hyper-CTL star now still works. Okay, and lastly,
we need to start wrapping up because we need to leave some time for questions.
Yes, I will be done in like 2 minutes. Thank you. So the last step in the hierarchy, hyper QCTL star, then becomes as powerful as monadic second order logic, and that means we're undecidable again. So let me just summarize. The picture as we know it from trace logics is that everything is decidable. We have LTL and then the extension to QPTL, and this has decidable model checking problems, also decidable satisfiability problems because of the correspondence to automata, and the same holds for the branching time logics. Now, in the hyper version, the problem is a bit more sophisticated. So the model checking problem stays decidable in the linear time world up to hyper QPTL, in the branching world up to monadic path logic. And the satisfiability problem, of course, becomes undecidable even for the smallest logics we talked about, although the better picture would be say that it depends on the quantifier structure that you see in the formula. All right. My second part is now being limited to one slide. So we have built various tools based on these ideas. There's MC Hyper, which is a model checker that verifies hyper LTL specifications against systems given as circuits. There's EA Hyper, MG Hyper, which are satisfiability solvers based on this construction. MG Hyper is actually an incomplete construction that also works in the undecidable fragment, but of course is not complete. RD Hyper is a runtime monitor that repeatedly solves the model checking problem as we learn more about a system we observe. And HyperBOSI is now a synthesis tool that uses constraint solving to find an implementation that satisfies a given specification in hyperproperties. So let me just wrap up by saying that I think this is an exciting class of properties, and we're in a very fortunate position in terms of the decidability of the model checking and satisfiability problems. The model checking actually is solvable for a very large fragment of this hierarchy that covers most properties of interest. Satisfiability is only decidable in this exists for all fragment, which however covers many interesting cases. And I think that there is some exciting future work to be done. In particular, there are many more hyperproperties that are still not clear how to express them in these logics. So we will need much more development in order to show to unveil the full landscape of hyperproperties. Thank you very much. I'm sorry I ran a little bit out of time, but I thank you very much for your patience. And I would very much appreciate it if we still have some time for questions and comments.
As we usually say, let's thank the speaker. I have no idea how to do it in this setting, but okay, any questions? There is the possibility, by the way, to ask questions in cloud. None of you have chosen it, so if anyone has a question he wants to ask, online, that would be the time.
I can maybe just fire off. Sorry, thank you, Bernd. But just a quick question. You had different classes of Kripke structures and different results. I mean, trees and DAGs and general ones. I mean, you know, trees are extremely structured, and DAGs are already spaghetti code, and you know, general graphs are spaghetti code with loops, which is like nightmarish. So, is there like you know, a classification or some results or something to exploit when it comes to like DAGs with bounded tree width? You know, like trees are, you know, tree width 1, you know, and many systems, at least program systems, have a very low tree width because they're built up modularly. Is there is that an index into the set of, you know, as a parameter into the problem?
Sure, there is. I don't think anybody has written this up, but yeah, I completely agree with you. So, I mean, the motivation for those results is actually that they came out of an analysis of the runtime verification algorithms where you do have trees. But I would suspect that you know, you find that this is a smooth index that that could be applied to the tree width.
Thank
you. Related to that question, if I may, so the tools that you presented, how do they scale regardless of this restrictions in input? So if you're not dealing with runtime verification and you have a full-blown circuit, can they support different clock domains or stuff like that that can cause like different variations in traces that requires different synchronization? How do this work for that?
Okay, so at the base layer, what MC Hyper does is it reduces the model checking of a hyper property to the model checking of a trace property, and it does that by creating a new circuit. For example, if you have for all property, then it just creates 2 copies of the circuit and builds a monitor on top of that ensures that their behavior is appropriately related. And then with that new circuit, it goes into standard verification techniques, say IC3, interpolation, what have you, right? And this means that it scales exactly as well as the underlying verification technique, which is pretty good in most cases, right? So if it's amendable, say, to bounded model checking, then and the error is not too deep, then you get very, very good results even for huge circuits. Now, the problem arises when you have a for all exists quantifier alternation, because obviously a complementation is nothing that would work in practice. So what MC Hyper does then is it approximates the complementation with a game. So rather than having a full representation of the quantifiers, it plays a game between one player that represents the universal quantifier and another game that plays the existential quantifier. Now, if you find a winning strategy for the existential quantifier, that's beautiful. And that can be done reasonably quickly. However, if you don't find such a winning strategy, that doesn't mean that your property is violated, and then you essentially give up.
Thank you. More questions? Okay, so we thank you again for a lovely talk, and then I'm handing off the session to Grigory.
Thank you. So, welcome to VMCAI once again, if you've just joined. We'll begin with technical talks. So we have a session on hyperproperties. There will be 2 talks, 15 minutes each. And so the general strategy actually is to go for 12 minutes talk and then 3 minutes questions. So please prepare questions in advance. So go to CrowdR, and if you have a question, you just type it and I will read it in the QA session. Don't wait till the very end. I guess it will be convenient for all of us. So, and the first talk in this section will be given by Ohad. and about compositional model checking for multi-properties. So Ohad, please unmute yourself, and the floor is yours.
I hope that everyone sees the presentation. Yes. Okay.
Yes, we see it.
Great. Hi, I'm Ohad, and I'm going to present the work on positional model checking for multi-properties, which is a joint work with Orna Greenberg and Sarah Schoenwald. The work composes of two algorithms. One is based on abstraction refinement, and another one is based on automata learning approach. And both are uses compositional methods in the model checking algorithm. The basic kind of properties are trace properties, which allow us to refer to each trace in the model separately. For example, we can say that every trace in the program satisfies P in 2 consecutive states, but trace properties are not expressible enough when we want to consider more complex properties, and then we need to use hyper properties, which allow us to refer to different executions of the same problem simultaneously and relate between the different traces. Hyper properties, for example, can be, one example for a hyper property can be that there is no information leak from high variables to low variables. In this setting, we have two kinds of variables, high variables and low variables, and we want to make sure that there is no information, no propagation of data from the high variables to the low variables. If we want to say this in a hyper property kind of way, we say that in every 2 executions of the same program that are given the low actions, the low variables are also always equal. And this is an example for a hyperproperty which is useful for security verification, and many other hyperproperties are also so. And we usually use hyper-LTL for describing hyperproperties, and this kind of property will be given as for every trace pi and for every trace tau. If both traces agree always on their low variables, then they also always agree on their low output variables. And the problem of hyperproperty model checking is given a model M and a hyperproperty P to determine whether the model satisfies the property or whether it doesn't, and then, if possible, to give a counterexample. And the algorithm usually composes the model with itself and the property many times, as much as quantifiers in the formula, and checks for emptiness. But since we need to compose the model with itself many times, for large models or complex properties, the problem becomes unfeasible, and we want to reduce the state space. An approach to do that is abstraction. Given an abstraction, we want to approximate the original model and consider a smaller one which removes unnecessary details, and we want to be able to deduce information from the abstraction to the model. Specifically, if the abstraction satisfies the property, we want to be able to deduce that the original model also satisfies the property. And usually there are 2 kinds of abstraction. The first one is an over-approximation, and which includes all the traces from the original model, but might include additional traces, and is useful when the model is quantified by a universal quantifier. And the other one is the under-approximation, which contains a subset of the traces from the original model, but no other traces, and is useful when we want to check an existential property. But when we want to consider a more complex property, which includes a quantifier alternation, we cannot use either an over-approximation or an under-approximation and get sound results. So in this case, we cannot use a simple approximation. Another problem with hyperproperties is the fact that it's hard to express properties that relate between different models. For example, if we want to say that 2 programs P and P prime are equivalent, we cannot naturally express this in hyperproperties. It is possible, but we need to build a complex model that includes both of them and allow us to differentiate between the traces. We extend the notion of hyperproperties to multi-properties that allow to refer to runs in specific models at once, given as a tuple of models. And we define multi-LTL, which is an extension of hyper-LTL that introduces indices for the quantifiers, which means from which model we take the trace. For example, the following property says that from every trace from the model M1, there exists a trace in the model M2, such that if both inputs are the same when we begin the execution, then when both traces end, the output is also the same. And our first algorithm is for multi-LTL model checking and is based on abstraction refinement. Firstly, we showed that multi-LTL model checking is polynomially reducible to hyper-LTL model checking and vice versa, which means we cannot expect to achieve better complexity than hyper-LTL model checking. But in contrast to hyper-LTL, multi-LTL is also compositional, which means that when a model is quantified by a universal quantifier, we can add traces and consider an over-approximation. And when a model is quantified by an existential quantifier, we can remove traces and consider an under-approximation. This compositional approach allows us to consider compositional proof rules for the model checking problem of multi-LTL. So given a model checking problem of multi-LTL, we create a set of abstraction, AI for every model MI, such that for every universal quantifier, we consider an over-approximation, and for every existential quantifier, we consider an under-approximation. And if we can show that the abstractions satisfy the property P, then also the original model satisfy the property P. And symmetrically, we can consider a similar proof rule for the refutation of the satisfaction. As I said before, the first algorithm is based on SIGAR and abstraction refinement, in which given a model checking problem, given models and a multi-LTL property, we first generate an initial abstraction and perform the model checking. If the model checking succeeds, then we conclude that the model satisfies the original property. And otherwise, we generate a counterexample and check whether it's spurious. If it's not spurious, then we find a real counterexample and we can conclude that the model does not satisfy the property. And otherwise, we need to refine the abstraction based on the counterexample found and return to the model checking phase and continue as before. The main problem when considering the SIGAR approach for multi-properties or hyperproperties is the part of generating counterexamples, since counterexamples may not always exist for multi-properties. So consider, for example, the property P1, which is a universal property, meaning that all quantifiers are universal quantifiers. In this case, the counterexample is a tuple of words, W1 up to WK, such that these words together does not satisfy the property phi, and each WI is from its appropriate model. But when we consider the property P2, which uses an existential quantifier, when a model does not satisfy it, we know that every trace in the model is a bad trace, meaning that the entire model is the counterexample. And therefore, the general case, the model checking cannot generate a counterexample for general multi-properties. But we can consider a counterexample in a subset of properties of multi-LTL. So for properties which are for all exist fragment, meaning that there is a sequence of universal quantifiers followed by a sequence of existential quantifiers, we can extract counterexamples from the model checking for the universal quantifiers when we fix all the existentially quantified models. And then we can refine the original models using those counterexamples. And this is very useful since many security properties are of this form, and it is very useful to be able to deduce counterexamples from the model checking procedure. But for the general case, we cannot obtain counterexamples from the model checking, but we can use a heuristic to create the counterexamples, which means that we take from each model and abstraction a trace that is only in one of them, meaning that it's or in the model and not in the abstraction, or that it is in the abstraction and not in the model. And in this way, when we perform the refinement, the abstraction becomes more precise, and we get closer to the original model if we didn't succeed before. And the second part of the work is for terminating programs modeled as automata, and then the multi-properties are also modeled as a multi-hyperautomaton and are also regular properties. In this kind of framework, we use the L-star algorithm in our model checking technique. So the L-star algorithms aim to learn a deterministic finite automaton for an unknown regular language U, and it uses two kinds of queries. The first one is a membership query, which checks whether a word W is in the unknown language U, and the other one is an equivalence query, which checks whether a candidate DFA is such that its language is the unknown language U. And when we need to use this algorithm in the model checking, we need to implement both membership and equivalence queries. And also, when we use the L-star algorithm in the model checking, we usually aim to construct the weakest assumption, which is the most general language that allows us to conclude that a model satisfies the property. In the general case, however, weakest assumptions does not exist for general multi-properties, but when we consider the universal existential fragment, then we can define a weakest assumption and use it in the model checking. So given a property quantified by for all exists and then multi-model M1 and M2, the weakest assumption is the union of all languages of automatas A such that A and M2 together satisfy the property P. And we showed that this weakest assumption is regular, which means that we can aim to learn it using the L-star algorithm. And also we showed that given an automaton A, its language is a subset of the weakest assumption if and only if A and the model M2 satisfy together the property P. So when we consider this model checking problem, it is enough to find an approximation A such that it contains the language of the model M1 and it is a subset of the weakest assumption. And then we need to implement two kinds of queries. The first one is a membership query. Given a word W, we want to determine whether it is in the weakest assumption. We construct an automaton A W with the language that contains only W and check whether it and M2 satisfy the property P. And for equivalence queries, we first check that the language of M1 is a subset of the language of the approximation A. And if so, we continue and check whether A and M2 together satisfy the property P, which means that A is a subset of the weakest assumption, and then we can conclude that the model satisfy the original property. In conclusion, we generalized the notion of hyperproperties to multi-properties and multi-model and suggested compositional proof rules for the model checking. One is based on the abstraction refinement and specifically the Seeger framework, and another one is an automata learning based using the L-star algorithm. And in both algorithms, we suggest an improved version for all exist fragments of the properties. Thank you.
Thank you. So we have one question, crowd R, perhaps related to notation. So the question is, what is meant by high variables and low variables?
So when we consider the secure information flow hyperproperty, the original model contains different kind of variables. The high variables are the secret variables. For example, a key that is used to calculate a kind of random noise. And the other variables are the low variables, which are observable to the users. And when the high variables are a password or a key that we don't want different users to be able to observe them, then we want to make sure that there is also no information in this form.
Okay. So any other question? Right now, you perhaps can unmute yourself if you want to ask Ohad something. So we have 1 minute till the next talk, so we can use that. Bernd?
Just quickly, do you have a complexity analysis for the construction of the assumptions in the compositional approach? I would think that a learning approach might have advantages over an explicit construction because you scale in the size of the necessary assumption.
Since we consider different abstraction for different models, the analysis for the abstraction construction is a polynomial and is always polynomial in the size of the original model. So, for example, when we take the different models, for every one of them, we construct an abstraction using pretty standard approach for constructing abstractions for CTL or LTL model checking.
All right, and the learning-based approach? And
in the learning-based approach, the L-star algorithm is polynomial in the size of the final learned the DFA. When we don't know, and we need to consider also the complexity of the different kind of queries. So the membership query might be is a polynomial, but the equivalence query, since we use the model checking query inside, is exponential, and therefore it's pricier.
Thanks very much.
Okay, let's thank the speaker again, and we'll move to the next talk and also the last talk of this session. Eric Koskinen will be talking about data structure commutativity. Let's go ahead.
Okay, I assume everyone can see my slides. Okay, great. So I'm going to be talking about our recent work on verifying commutativity. So as we all know, there's an ongoing need for programming models and compilation strategies to exploit concurrency. And it's also well known that data structure commutativity is a strategy for enabling concurrency. This goes back to the databases community, as well as the parallelizing compilers community. And then over the past decade or so, there have been even more algorithms and techniques for transactional memory, runtime systems, and so on that exploit commutativity for concurrency. So commutativity, to be precise, we're talking about data structure commutativity, and that is circumstances where from a given state and arguments to some functions, if you were to apply the methods in either order, you would reach the same final state and observe the same intermediate return values along the way. And why does this enable concurrency? Well, roughly speaking, if we know there's a circumstance, such as, let's say, x not equal to y, under which two operations commute, like modifying a hash table, then running those operations sequentially is sort of equal to running them concurrently. There's some important side conditions that I've elided here of linearizability or atomicity, but I won't cover those during this talk. So let's look at an example. Here's a really simple data structure of a set that stores two natural numbers in it. It does this with integers a and b. So initially we'll mark them as -1, indicating that nothing is stored there. Add just looks for an available slot to put its argument into. Isin checks whether its argument is stored either in A or stored in B, and so forth. So commutativity condition is a logical formula such that if for all states and argument values, the formula holds, then that means that M and N, methods M and N, will always commute from that state. So a simple example, if we consider the methods isin commuting with itself, we can just use the logical formula true for that. Those methods don't modify the data structure in any way. And so we can just, they always commute. So looking at a more tricky example, isin and add, these will commute in 3 different circumstances or disjuncts. The first is when the parameters are distinct. They will also commute if they're operating on the same parameter. However, that value that's being added is already stored in A or is already stored in B. Note something about this data structure is that for a given abstract state, there are multiple concrete states. We'll come back to that. And then we can write down for all other pairs of methods, we can write down a variety of commutativity conditions. To give one more example, consider the simple 101 array stack where you have an array of values and a cursor top, which is the index of the topmost value of the stack. And then you just have push and pop in the usual way. Here, a commutativity condition for pop and push is that there has to be at least one element already in the stack, and the value that's on the top of the stack has to be the same as the value that's being pushed onto the stack. And also there needs to be enough space in case the push happens before the pop. And we can write down, again, other conditions for the other pairs. So since the variety of parallelization strategies I mentioned earlier depend on these commutativity conditions being sound, the work that we're interested in here is on verifying these commutativity conditions. So we start by asking whether we can do this in some automated way. We'll talk about a reduction to reachability. But then we'll see that tools can struggle on that, and we'll look to try to understand more semantically what's the appropriate abstraction for commutativity. And then we'll use that in an improved reduction. And then finally, I'll talk a little bit about our implementation and evaluation. Okay, so let's start with this example and try to prove commutativity. And we can begin considering as a simple two-safety property. Let's try it with the stack example and the commutativity condition that I mentioned a moment ago. So I have here a sort of product program where on the left-hand side, we've seen one scenario where you perform push followed by pop, and this will act on the state sigma 1. And on the right-hand side, you'll see the other scenario where we perform pop followed by push. So we, furthermore, in the pre-relation, we assume that the commutativity condition holds and that these two states, sigma 1 and sigma 2, are equivalent. And now we're going to try to verify that the return values along the way will agree, as well as the fact that the final states will be equal. Well, if we do this, unfortunately, depending on the order, we'll get different concrete post states, right? Because the sort of extra garbage to the right of the top of the stack will be different depending on whether the pop happened before the push or vice versa. So the issue here is that just using sort of concrete equality on the post conditions is just going to be too strict. So, well, you might say, well, why not we use specifications and use that as our post state notion of equality? So this idea of using specifications is what was done in prior work, such as PLDI 2011 and TACUS 2018. So let's try that out. Well, maybe why don't we try specifications like true, which is a certainly fine coarse-grained specification. The problem there is that it seems like all post states are related if you use true as your abstraction. And in fact, if you were to use the TACUS 2018 work, it would incorrectly synthesize an unsound commutativity condition because it's based on these specifications. And the issue is that these specifications don't capture the effects of push that are relevant to commutativity. Meanwhile, we could kind of go to the other extreme and do very fine-grained, precise specifications. But this starts to border on sort of full functional verification. And a lot of those specifications involve reasoning about parts of the data structure that are actually irrelevant to commutativity, such as the deeper portions of the stack. So this brings us to the key insight of our work, which is to try to understand better what is the right abstraction for commutativity. And we start by observing that the precision needed depends on the methods that are under consideration. So if we're considering simple set and is-in and clear, we actually don't care about the value of size or SZ, that extra variable. We only need to reason about whether or not Y is stored in A or stored in B. And we can do this with simple predicates, A equals Y and B equals Y, as well as their negations. And not only does this abstraction ignore size, it also ignores all other possible values for A and B and just focuses on what matters for commutativity. To look at the array stack example, the abstraction that we'd like is something that only considers the top value and ignores the deeper values of the stack that are going to be the same regardless of whether pop happens before push or vice versa. So how do we characterize this appropriate notion or degree of precision for commutativity reasoning? And what we describe in the paper is this concept that we call MN differencing abstraction, which is to try to precisely characterize what's needed to have enough precision to reason about return value agreement. So the full formal details are in the paper, but the intuition is that you have an abstraction alpha and then a relation in that abstract domain that must be precise enough to characterize states that originated from the same state and agreed on return values along the way. We then describe what it means for a commutativity condition to imply an MN differencing relation. And there, the intuition is that the commutativity condition is strong enough that it will ensure that return values will agree, and that this relation or alpha will capture all such post states. So let's look at an example. Back to simple set we saw before. Again, same predicates. We can just think about using these predicates that determine whether or not A is equals X or B equals X. And then the relation can be about agreement on the valuations of those predicates, whether the two states agree there. So then given our commutativity condition, we can then show that this will imply that relation in the post states. Meanwhile, for an array stack, we can define our abstraction in terms of predicates that capture whether or not the value at the top of the stack is equal to X. And the relation is about agreement on those predicates. So then we need to address equivalence in the post condition of the relation. And to do this, we use an observational equivalence relation, I sub beta, I'll subscript at beta to make it clear that this can be over a different abstraction, beta. And so when you put these all together, it leads to a proof rule that decomposes the overall goal of proving commutativity. I won't have time to go into details, but they're in the paper. So next, we describe a algorithmic verification technique that reduces this to reachability. So this takes as input the implementation of a data structure and the methods of interest, and it will emit an automaton such that the safety of that automaton implies that phi is a commutativity condition. And this is like the two-safety product program we mentioned a moment ago, but we further restrict the precondition to only reachable ADT states, and we ensure that you check observational equivalence in the post condition. However, tools struggle on that a little bit, so we then introduce a second reduction that employs this MN differencing abstraction, and it actually emits two automata. The first or the second, A sub B, encodes the proof, the part of the proof which involves showing that I is an observational equivalence relation. And then the other part, A sub A, encodes whether or not a given commutativity condition implies R alpha and that R alpha implies I. So the important thing here is that we can use different abstractions for these different purposes, and we can actually reuse A sub B for any pair of methods and commutativity conditions. So every time we have a new query, we can reuse A sub B. So we implemented this in a tool called CityProver. It takes as input the implementation of an ADT and a candidate commutativity condition, and it emits these automata that then are reachability tasks that a solver like CPA Checker or Ultimate can be applied to. So first we applied this to some really basic data structures like a single cell memory, an accumulator, and a counter. We looked at a variety of method pairs. We wrote down commutativity conditions that we expected to hold, as well as ones that we expected to find a counterexample for. And in most cases, under either the reduce or the DA reduce reduction, we were able to prove the property quickly with either CPA Checker or Ultimate, typically within a couple seconds. There's one case where it timed out. We then turned to the simple set and array stack, as well as an array implementation of a queue and a hash table, and looked at a wider variety. And here we'll see that started to take a little bit longer. We saw more timeouts happening, and in some cases, some memory outs. We mostly used Ultimate, but in some cases when Ultimate struggled, we switched to CPA Checker, and those are the ones that are marked in blue. And generally, DA reduce seems to perform a bit better than reduce. It suffers from fewer timeouts or memory outs, and also it typically will return an answer sooner or perhaps much sooner than reduce. So as a quick summary, the observational equivalence relation was sometimes inferred, and in those simple ones, and the other cases we provided it. In all cases, however, the tool was able to synthesize the appropriate abstractions that were needed and the differencing relation. We were able to take advantage of the fact that we could just run verify A sub B once for each data structure. And most could be proved in a reasonable amount of time. Our timeout here was 600 seconds. Reduce, as we saw, struggled in many cases, and DA reduce was better. So for example, with simple set, it's roughly 3 times faster, 3 or 4 times faster. And as we saw, DA reduce has some overhead, but not as many timeouts or memory outs. So one lesson that came out of this is that this works well for collection classes that store values in fixed locations, and ADTs that have a lot of permutation in them lead to blow up in disjunctive reasoning, which is challenging for existing reachability solvers. So in conclusion, we described a way of decomposing commutativity reasoning using what we call MN differencing. We discussed a few reductions to reachability, as well as our tool called CityProver, soon will be released. And in the future, we hope to investigate ways to scale this to bigger ADTs and also integrate the output into tools that consume these commutativity conditions. Thank you very much, and I would love your questions.
Thank you. I have a question from Andreas Podelski. Is there a difference whether one checks commutativity in the context of parallelization or in the context of partial order reduction? Make a sequential program concurrent or make a concurrent program sequential?
So it certainly simplifies matters to verify commutativity in the context of a sequential program. And that's kind of the strategy we're employing here, that as a kind of orthogonal issue, you first verify it sequentially. In the context of partial order reduction, I could see that being useful too. We haven't explored that, but that's very interesting. Yeah, I mean, in terms of the strategy that we use here is just about being able to reorder segments of code and the preconditions that are necessary for those segments. So I could imagine that being incorporated somehow into some kind of partial order reduction algorithm where you're given a couple traces and you're trying to see where classes of traces and see whether you can collapse them into the same equivalence class with commutativity. So in short, I'm not sure, but it sounds interesting.
Okay, so I think we are over 3 minutes over. I think that the discussion should go to breakout room or somewhere else. Let's send the speaker again, and that concludes the session.
Thank you very much.
So we'll have a break until 1800 hours CET. We'll leave the room open, so you can just hang around here if you want to. I'll turn off the recording now,